Okay, so the first question, we're just going to talk about a little bit, get introduced to what internal flow is. I'm sure you've seen it in class. This is just a fairly simple question. Just talking about flow, and then we'll talk about heat transfer. So internal flow means it's in a pipe, maybe it's in a duct. A lot of you guys are in building engineering, so that's maybe more interesting. But so this question is fully developed laminar flows in a circular pipe. The velocity is at r/2. So velocity in the middle is measured to be 6 meters per second. And we want to determine the velocity at the center of the pipe. Sorry, the velocity midway between the center of the walls. So draw this quickly. So we have a pipe and we have our boundary layer. So unlike in the last section where our boundary layer was kind of just on one side of a sheet, this time our boundary layer is fully in. So now we don't really have a T infinity like we used to. And some of the equations switch around. All the cases are different. So the thing you use to find your Nusselt's number, all those are different, but all the principles remain the same. Essentially, find the case that's similar to what you're dealing with and solve. So we know our equations. This is true for pipes. Our velocity at any r is equal to our maximum velocity times 1 minus r squared. So this r being the one we're interested in and the big R being the actual radius. And in this case, we know that our V max is also the center of the pipe. That's just by definition, this is a velocity profile, and so our maximum velocity is going to be in the middle. That's what we're interested in. And we know our velocity at r/2. So our velocity at r/2 is equal to V max. All right, and then so we know that our VR is equal to this 6 meters per second. So our V max equal to 4 which is 8 meters per second, which was our answer. So this is just getting you used to internal flow. I guess. Not a very difficult question, but nice way to ease us into it. Oh, sorry, I moved on from that very quickly. Give you guys a second. Any questions about this one? Okay, so we'll move on. Okay, so now we're getting a little more advanced here. So we have oil, it's flowing through a pipe 10 degrees Celsius of 40 centimeter diameter. The pipeline has an average velocity of 0.5 meters per second. So as we know, the velocity here is going to be less than the velocity in the middle, but we're given average velocity this time. At 1500, or there's a section of it, a 1500 meter long section that passes through an icy lake. And they say that the lake is icy, so it's at about 0 degrees Celsius. And we also know that the surface of the pipe is at about 0 degrees Celsius. So that's the outer surface. And then they say disregard the thermal resistance of the pipe material. So if we were to draw a cross section, what we're saying is that if this is 0 degrees Celsius, we're also going to say the inside of the pipe is 0 degrees Celsius because we're disregarding that thermal resistance. So we want to find the temperature of the oil when the pipe leaves the lake, the rate of heat transfer from the oil, and the pumping power required to overcome the pressure loss. Okay, so the first thing we're going to do is similar to in the previous section, we're going to just collect all of the properties, and we're going to find them on table A13. And normally we'd want to use the bulk mean. So if we knew what the temperature was going in and we knew what the temperature was exiting, then we would use the average. But in cases we don't know, we have to start here, and then if the question asked for it, we could iterate it. So we could find it and then restart. But typically you would just use the entry. So that looks like a B. That was supposed to be 13. And from this table, we'll get density. Mu. Our heat capacity. Conductivity. Viscosity. And our Reynolds number. Okay. So the first thing we'll find is our Reynolds number. And for each shape, there's a different Reynolds number, or it's all mostly the same equation, but we use our hydraulic diameter. And in the book, they'll show you the hydraulic diameter for a whole bunch of different shapes, but for a circle, it is the diameter. So that's nice and easy. Right, and last time we said it was about 10 to the 5 was our transition from turbulent into laminar. But because we're talking about internal flow now, these kinds of criteria change. And so what we're looking for is less than 2300, which it is. And because it is, we know, I shouldn't write that there. This would create it, make it turbulent, so this whole flow is laminar. All right. So the next thing we find is our entry length. So there's a thermal entry length. This kind of length where I think is where heat transfer doesn't happen, so our thermal entry length. So it's just a rough estimate. As the fluid will enter into the 0 degree situation, we'll just take some time for the heat. So like with this whole chapter, there's an equation for that that's specific to laminar flow. times our diameter. So we have our Reynolds number. We found our Prandtl number off the table. And we know the diameter of our pipe. So we can find this at 44,367 meters. All right, and so because this period of time where the flow or where the heat transfer is developing is much longer than the total length of the pipe, we assume that it's thermal developing flow, which again will lead us to our specific equation for Nusselt's number. So we have to go through all this criteria to determine what Nusselt's number we use. So similar to last chapter, but a couple more steps. So because this is greater than the length, just write this down, we so this gives us our equation for Nusselt's number, which by definition is Hg over K. And the correlation we're going to use is 3.66 plus this will give us 13.73. So our Nusselt's number is our correlation to our average heat transfer coefficient. So that gives us our H. So K we got from our table. All right. So that was all to find our heat transfer coefficient. Now we can go ahead and find the exit temperature of the oil. And to do that, we're going to use our logarithmic mean temperature difference. So as the oil flows along the pipe, it of course loses temperature. And so we can find that with this equation. So we have our mass flow rate, and we know how fast our oil is going through our temperature, our pipe, and we know our surface temperatures. So again, we're trying to figure out, we have our average temperature at the start, we're trying to figure out average temperature at the end, and we know this internal surface temperature is at 0 degrees Celsius. We know our initial temperature is at 10 degrees Celsius, and so we can use this equation to find the temperature through the pipe. First, we have to find our m dot using our mass flow rate. First we need to find our m dot. So we're going to do that with the properties we know. So we know the area of our surface. So first we need to find area of the surface, then we need to find m dot. So this is pi dl. Now we need to find m dot, which is our density times our volumetric flow rate, which is our density times the area of our cross section. So I'm going to just write that. So this would be this area times our average velocity, which we're given. So we're just going to incorporate our area into here. We'd find a mass flow rate of 56.15 kilograms per second. So taking both of these and plugging them into this equation, we'll get 0 degrees Celsius minus 0 degrees Celsius minus 10 degrees Celsius. So another one of those situations where because we're dealing with a lot of differences, we're able to use our degrees Celsius, but if you're ever unsure, you can always use Kelvin. Kelvin will always be right, and degrees Celsius is right if it's the same as your result if you're using Kelvin. All right, and plugging in all that, we get our exit temperature of 9.13 degrees Celsius. So if you haven't reviewed this yet, it's probably a little hard to follow because, again, we're just kind of using the right equation for each case. But hopefully having lots of examples to study from and then reviewing the textbook will help you review. All right. So there were 3 parts to this question. Okay, so we found the temperature of the oil and leaves the pipe, so now we need to find the rate of heat transfer of the oil. Sorry, this answer is not super clear. Okay. Perfect. And then the pumping power required to overcome the pressure. Okay, so now here, so part B, so here is actually where we use our log mean temperature difference. And this is because for this situation, we can find our Q dot is equal to our H, which we've calculated, our surface area of our pipe, times our delta T, but specifically the log mean, because we know that our temperature varies throughout the pipe. So our log mean temperature is equal to temperature at our exit, which we now know, temperature at our inlet, so this will give us a log mean temperature difference of 9.56. So we can find then our heat loss, our total heat loss throughout the pipe, H. Oh, I've already written that. So we know H now, we found surface area in the last part of the question, and we've just found our log mean temperature difference, and we'll get a total heat loss of 90.3 kilowatts. And then the final thing we're finding is our pressure drop, part C. And so this is just purely getting into fluids. So we know we have laminar flow, and so we know that our pressure drop is equal to our friction coefficient, L over D. And again, this is specifically the equation for pressure drop across the circular pipe. All right. So we know pretty much everything. We know the length of the pipe, the diameter, the density we got at the beginning when we read the properties, our average velocity. The only thing we don't know is our friction coefficient. So we know that our friction coefficient for, again, laminar flow, so 64 over our Reynolds number. This is equal to 0.8294. Plugging all that in, we'll get a pressure drop of 347.4 kilopascals. So definitely the main thing to focus on is this heat transfer part. But it's also important to know a little bit about pipe flow when you're doing this. So we need to learn a little bit about Reynolds number and friction coefficient when we're doing heat transfer. And then this question also asks about change of pressure. So that was a little hard to follow. I think that's understandable. There's a lot of just, this is the right equation to use in this spot. So it's, yeah, definitely something to review as you go through the book. But we found first that it was laminar. We found then that it was a developing flow. And using those two pieces of information, we're able to find which Nusselt's number or which Nusselt's correlation we're using. Then we're able to find the temperature oil at the exit using this equation, which again is specific to when we have a fluid flowing through a pipe. And then we found, again, our log mean temperature specific to fluid flowing through a pipe. And using that, we were able to determine our heat loss. So that's a lot, but any questions about that now? And keep in mind that you're able to ask me more, or you're able to email me with questions if they come up later. Oh. Sorry. Okay. All right. So we'll do one more question, and the idea here is we'll just get a little bit more exposure to a different kind of question, and then we'll be all done. I know it's a little hard learning new stuff when you have the midterm coming up based on the old stuff, but here we are. So in a food processing plant, hot liquid water is being transported through a pipe. So this time we're given conductivity, inner and outer diameter and length. We know the mass flow rate, so we're given a little bit more things this time. We don't need to calculate as much, which is nice. We know it enters the pipe at 100, exits at 60. So now we're going to be able to use that bulk mean temperature. So the plant supervisor thinks that since the hot water exits at the pipe at 60 degrees Celsius, the pipe's outer surface temperature should be safe from thermal burns. In order to prevent thermal burns from an accidental contact, the outer surface has to be kept at around 45 degrees Celsius. So we're just trying to determine what that outer pipe temperature is going to be and if it's going to be more or less than 45 degrees Celsius. All right. So similar process. So for water, it doesn't say, oh, there's table A9. Never mind. So we're going to go to table A9 and we're going to get our properties for water. And this time we're going to do it at our bulk mean. Temperature. So 100 plus 60 over 2. Which is 80 degrees Celsius, and then that's where we're going to get our properties for. So again, we're going to get our CP. $197 joules per kilogram Kelvin. Okay. Friction coefficient. And finally, our Reynolds number. All right. Starting the question now, our Reynolds number, same as last time. Okay, so we're using a slightly different version of it, the one that involves mass flow rate. And friction coefficient, or sorry, this is not the friction coefficient. That is mu, which is, I think it's the inverse of viscosity, or viscosity and viscosity and density is wrapped up in this. So with some conversions, you'll find that this is the same equation we used last time, just in a converted form, using the things that we need. And we're given mass flow rate in the question as well as diameter, and then we just found this for our water. So we're going to get our 21, 50, 20. This is greater than 10,000. So I'm afraid I didn't review this section as perhaps closely as I should. So in the last question, we said 5,800. This one, we're saying 10,000 is our condition for our turbulent flow. So it must be that with different fluids, we have different Reynolds numbers. So there's likely information about that. A table somewhere in your textbook, maybe the same one we brought up last time. But in this case, we're talking about turbulent flow. All right. And now knowing that it's turbulent flow, we can find our entry length. This time it'll be a different equation because it's turbulent. So our entry length is roughly 10 times the diameter, which is equal to 0.25 meters. And that's much smaller than the length of our pipe, which was 10 meters. And so we're going to assume fully developed. So last time it was laminar and developing. This time it's turbulent and fully developed. So the cases or the treatment, the approach will still be the same, but the equations we're going to use are going to be a little different. So the Nusselt's number can be found under these conditions, so under the turbulent and fully developed. Which gives us 98.13, meaning that our, missing one thing here. So we have everything in this equation except for our friction coefficient. And again, this time we're going to calculate our friction coefficient using a different equation because we are talking about turbulent flow this time. Last time it was 64 over the Reynolds number. This time it's 0.79 ln of the Reynolds number. So plugging that into this will give us this 98.13. All right. So now we're going to use the same equation for our relationship between our interior, or between our fluid temperature and our surface of our inner pipe, using this equation. So this is just the same one as last time, but rearranged. Actually, no, it's not rearranged yet. All right, and if we solve this so we know our surface area, we can calculate that using So we know this, we were given m dot and Cp in the question, or sorry, Cp we found on the table. And then we know, unlike last time, we know our exit and our inlet temperature. And what we're interested in is this surface temperature. And keeping in mind that, unlike the last question, we're not neglecting this thermal resistance. And so we're finding very specifically our internal surface temperature. Which is 58.38. And the answer key I'm using rates it like this. It doesn't actually solve for our surface temperature. And it looks like that would be quite hard to solve for. So a lot of calculators have system solvers that will, you just can type this in and it'll numerically find your TS. So a good idea to know how to use that kind of thing. All right. And so once we have this surface temperature, and what we care about is our exterior temperature, we're actually all the way back to our chapter 3, our very initial kind of understanding of conduction. And we know from that the resistance, the thermal resistance of our pipe is 1. And the reason why it's not just a simple, as you remember, for a wall, we had a resistance, and there was none of this ln. It's just because we're in polar coordinates. We know that our heat transfer acts normal to our polar coordinate, and so that's where this ln comes from. So calculating this, we get 0.0001934 Kelvin per watt. And so the rate of heat transfer through our pipe is equal to our surface temperature on the inside of our pipe minus the surface temperature of the outside divided by our R of our pipe. And then one last piece of the puzzle. We also know that we also know the total amount of heat that's being released. So we know our temperature at our inlet, like we said before, and our temperature at our exit. And so because we know what our delta T is here, we're able to figure out how much heat was pushed out into this material, or Q dot, and then we're able, using that, we're able to figure out how much will continue to be pushed out through here. So in this case, we don't actually need this outer temperature, because rather than measuring our outer temperature, what we're doing is we're just measuring our inlet and outlet temperature. So hopefully that makes sense. So this is equal to our m dot Cp, so the heat capacity of our water, temperature of the inlet of our pipe, minus the temperature of the exit. So our surface temperature on the outside is equal to T, temperature on the inside, minus our pipe resistance, T inlet and minus T exit. So just reorganizing this equation above, it gives us 53.5 degrees Celsius. Okay, so just made it. Okay, so that's the last question we're going over.